we are looking at law of sine, law of cosine, and mixed here. These problems are going to be mixed. We don't know initially whether we're using law of sine, law of cosine. So if you have yet to actually practice the law of sine, law of cosine outside of a word problem, I'm going to put a link here on the screen so that you can go there and practice it just on a triangle first. But I believe if you've made it to this point that you know how to use both of these. So right now, a tree growing on the side of a hill casts a 102-foot shadow straight down the hill. Relative to the horizontal, the hill slopes at 15 degrees, and the angle of elevation of the sun is 62 degrees. All right, so looking at this, a couple of things to point out. We have a tree growing on the side of a hill. We have a length here that's cast down the hill. So what that tells us is with our diagram, because that's what I'm helping you here with, our tree, we say, is this segment. Our hill is sloping downwards, hence the shadow is going downwards. So this is 120 feet. Okay, so relative to the horizontal, the hill slopes at 15 degrees. That's new to us. We have yet to see one of those in a problem. So how do we interpret that? Well, typically, we say the angle of the ground is 0 degrees. Well, here the angle of the ground is not 0 degrees, it's 15 degrees. So typically we identify it as there. Well, the 15 degrees would tell us it's now there. Okay, so that's one thing. Then we're also told that the angle of elevation of the sun is 62 degrees. Now, what that even means? So that's because of the shadow. So we have a shadow, so the sun's over here, and the sun's casting a shadow. Okay, so the angle that the shadow forms from the horizontal, that's angle of elevations are from the horizontal, this angle is 62 degrees. Do not make the assumption that the angle with the ground is 62 degrees. The angle of elevation is always from the horizontal, even if our ground is sloped. So we have this. This is all we have, and they want to know what is the height of the tree. Okay, so this is our diagram. Let's work with it to get something that we can easily see what we have and therefore know what we're going to be using. Okay, so our triangle is going to be shaped like this. All right, so we know that this length is 120 feet. So, being at the two angles together, the 15 degrees and this other piece, the two together equals 62. We can subtract 62 and 15, and what we get from there is 47. And this 47 will be the angle with the ground. Just slide it up. So we get 47. Okay, that's our angle here. That's still only one angle. So where our maybe other angle comes in, because I can't just throw a side length one here, where our other angle comes into play, if our tree was not on a hill, the tree would, we assume, form a 90-degree angle with the ground. Well, okay, so if the ground was horizontal, it would form a 90-degree angle. Well, it's not, the ground isn't horizontal, we have this 15-degree angle here, so the two angles together, again, this is because we are on a hill. We have to consider that slope when we look at this base angle of the tree. That gives us 105 degrees. Okay? We're looking for the height. So we look at this, we notice we have angle, side, angle. So there is our law of sine. So with your understanding of how to set up a law of sine, very first thing we'd have to find this third angle and go from there. Okay, but the biggest thing I'm worried about is, let's make sure we understand this 15-degree angle of the slope, and that the 62 degrees angle of elevation is still from the horizontal up. So therefore, it's not actually in our end diagram because of the sloped hill. All right. So law of sine, continuing here to find our height. Let's look at the next example. Okay, let's see what we have here. The pitcher's mound on the women's softball field is 43 feet from the home plate, and the distance between the bases is 60 feet. Okay, and the pitcher's mound is not halfway between home plate and second base. Okay, we can make the assumption that the baselines are perpendicular to each other. Okay, so you might think, well, I need to understand baseball or softball to do this problem, where really you don't. So we don't know how far is the pitcher's mound from first base. So we have the pitcher's mound, we'll say right here. Step just a little bit. We have home plate, we'll say right here. We are told that the pitcher's mound is 43 feet from the home base. So home plate to 43 feet. Okay. And we are also told that first base, that the baselines are all 60 feet. Okay. We desire to know how far the pitcher's mound is from first base. So we desire to know this distance. And because we have this assumption that the baselines are perpendicular to each other, meaning that third base is over here somewhere, that the angle here with third base and home plate and first, that we have a right angle. Well, we can assume, since this is 60 and this would be 60 as well, we can assume that this base angle here at home plate is bisected. So since it was 90, it will be 45. Okay? And we can make that assumption that the angle is bisected because these two lengths are congruent. So we have this triangle, we see side, angle, side. That would tell us the law of cosine is needed. And from there, we can set it up and solve. It's not that bad. Just the biggest part of this question is understanding what we can do with this perpendicular idea, and that we can bisect that angle to get the needed angle in the problem. Okay, moving on. So last question. So law of two forces acting on a body to produce a resultant force of 70 pounds. So the resultant force is 70 pounds. One of the forces is 50 pounds and forms an angle of 67 degrees in 40 minutes with the resultant. All right, so one of the forces is 50 pounds, so we do not know the other, and that's actually what the question is. So forces here, we can just draw we have one force, because this would be the 50 degree or 50 pound force. And then we have our resultant, which is, we'll say is right there, sure, 70 pounds. Okay, we're told that the angle between this 50-pound force and the resultant, we're told that the angle between the two is 67 degrees and 40 minutes. All right, now how in the world do we get the magnitude of the other force? Again, keep in mind that the other force we're saying is right here about. Okay, so we want to know what is that magnitude. With vectors, the parallelogram approach is very useful, because here's what we can do with this problem. The resultant force, we know that we could find that, at least the location of it, by constructing a parallelogram out of the two initial forces. Okay, so we have this 50 pound, we have this 70 pounds. This upper side is really what we're trying to find. So when you look carefully enough, our diagram becomes this. That's what we have. And the unknown length here will give us the magnitude of the force. Now, dealing with this angle measure, okay, you have looked at how to convert degrees, minutes, seconds back to decimal degrees. I'll put a link here to take you back to review that real quick if you need to. But we can use the calculator will work with this if we remember how to input these symbols, the degree and the minute. So we see that we have sine, angle, side. So this is the perfect situation for law of cosine. All right. So you have a couple of other problems to work on in this review, but I wish you the best of luck with all of it, and I'll see you in the next video, and goodbye.